So the first page, okay. So the first page, just some basic instructions. Okay, we call it a report. You're going to be putting your treatment of these questions together in a report. And just some housekeeping, when you're putting your submission together, do it 2 separate groups of stapled pages, 1 set for me, for my questions, 1 set for John. And make sure you put your name and student number at the top of each group of pages. It's just a single submission to the Coursework Receipting Office. It's just a single submission as far as they're concerned, but do prepare your pages in 2 separate stapled groups so that we can mark them in parallel. We're not waiting for someone to finish with the coursework to pass them on to the other person. The due date, as you already know, it's on your calendar. It's Wednesday, the 7th of February, by close of business that day. And you go on Moodle or on the Coursework website. Here, you get your own personal cover sheet. Don't use someone else's cover sheet. It's got a barcode attached to you on it. So download that, fill in the details. The easiest way to submit them is just those standard A4 plastic wallets. Just pop them in there and put the cover page on the front. And maybe just 1 lick of sellotape across the top. I've seen in previous years people go way overboard and like seal them up. Okay? Yeah, but just one little stripe of sellotape across the top will stop them coming out. And do make sure you keep a copy. If you're handwriting your submission, don't submit your final copy before you've photocopied it or scanned it. All these printers, you can do a scan to email or scan to PDF. It scans it and emails it to your account. It's a simple way to just make sure you hold on to a copy of your work. Okay? We'll mark it as usual. We'll mark it within the 4-week return period, and we'll give you detailed individual feedback, as well as giving some general class feedback, which will probably incorporate model solutions. Now this carries 30% of the unit mark. The other 70% is on the summer exam. Half of the marks are going for number theory, half of the marks for the cryptography questions. And there's part marks shown in the brackets of the question, so you can see where the marks are distributed. Do take account of this paragraph here. We are not so much interested in the final answers as in giving you the opportunity to demonstrate your understanding of the unit. Okay, so that's the key thing to keep in mind. You want to convince me and John that you understand this material and use your submission to demonstrate your understanding. So we'll award marks according to how well you present correct solutions to all the questions, where your reasoning is clearly explained and justified, and accompanied with appropriate references to results from the unit. Okay? If you do use computer computations in your work, in general, you should include references to this and pay attention to any specific guidance about how to present your computer work within each of the questions. Okay? Read the questions carefully. You can get support from us in the lectures, in the tutorials. We've got standard drop-in office hours where we're always available. Or if you can't find us then, you can try dropping in any time, or in particular, if you want to email us and fix a particular meeting time. Okay. Any questions just about the general arrangements before we get into the maths? Okay. So I've got 4 questions on it. Some are straightforward calculation type questions. Some are deeper, more problem-solving questions that you'll need to think about a fair bit. The first question is a question about the Euclidean algorithm. And you see here, I've made use of the fact that everybody has a unique 8-digit number associated to them. It's your MMU ID number. Okay. So for the first question, I want you to split your ID number in half into 2 4-digit numbers and convince me that you understand how the Euclidean algorithm works by performing the Euclidean algorithm to find the greatest common divisor of those 2 numbers. Okay. So find the greatest common divisor, and also the other thing the extended Euclidean algorithm does is it provides you with the coefficients for Bezout's identity. The linear combination of the 2 numbers that is equal to their greatest common divisor. Okay. Part B, I want you to come at the greatest common divisor from another angle by giving the prime factorizations of your two 4-digit numbers, and by inspection of the prime factorizations, explaining how that confirms the value of the GCD you just found in part A. Okay, so to be able to explain the GCD in another way, not as the output of the algorithm, but as argued from their prime factorizations. C and D, well, C is about extending the concepts of greatest common divisor and Euclidean algorithm to when you've got more than 2 inputs, so going to 3 inputs. So it's a little general question here. If you're given 3 numbers x, y, and z, and let D be the smallest positive integer you can achieve out of a linear combination of x, y, and z using integer coefficients, alpha, beta, gamma. So I want you to describe how the Euclidean algorithm can get you that number D. If you know x, y, and z, how can you use the Euclidean algorithm to get that number D? And I want you to illustrate this with a particular example using your A and B, which are your two 4-digit numbers from your MMU ID, and as the third number Z, to use this number, which is 10,007, I want you to demonstrate it. Okay? So I want you have to calculate what the smallest positive integer you can achieve as a linear combination of those 3 numbers, your two 4-digit numbers from your ID and 10,007. Part D is where some of the later marks are available, but this is a bit of a harder question. You have to think about this. It's not so much just doing a calculation method that we learned in the unit. You have to think a bit about this. So, assuming that nobody makes any mistakes, it's true that everybody in the class will obtain the same value for D. Okay? And I want you to explain to me why that is the case. So, why is it that everybody, when they do these calculations, always gets the same number D as each other? And I've given you a task here. So it's something about the number 10,007, okay? See, A and B could be anything. I haven't inspected everybody's ID number very closely, but something about the number 10,007. And a follow-up question, what is the smallest number, Z, so smaller than 10,007, but still strictly bigger than 1, what's the smallest number Z you could use so that you would be certain that everybody in the class would obtain the same value for D, right? What is that smallest possible number? Now, you do know, okay, you don't know what everybody's ID number is in particular. You do know some general facts about the ID number. Everybody realizes the first 2 digits are the year in which you registered with the university. You first submitted your application or whatever. So most people here have a number 16 something 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 or 15 something something, because most of you applied in 2016 or 15. Few people have an earlier number because they were involved with the university earlier to that, okay? So you can assume that everybody's ID number, if you interpret it as just an 8-digit integer, it lies somewhere between 13 by 10 to the 6 and 1 less than 17 by 10 to the 6, okay? So that's all you know, and you shouldn't assume anything else. You shouldn't go asking each other what each other's ID numbers is. So just based on this knowledge, what's the smallest number Z that you could find, and so that you would be certain that everybody would get the same value? Okay, better hurry up to give John time to explain this. Question 2. Again, it begins with something straightforward, which is following some examples we did in the course. And again, using n as your whole 8-digit ID number, interpreted as an 8-digit integer, what is the remainder that you get when you divide 2017 to that power by 51? So 2017 to that power is a gigantic number. It's outside the range of something that MATLAB can normally deal with. Okay, but what is the remainder that you get when you divide that by 51? And B just goes kind of crazy. It asks you the same question, but this time about 2017 to the power A. And A is itself 2019 to the power of 2021 to the power of your big 8-digit number n. So this number, 2017 to the power A, is just truly enormous. Far bigger. Any kind of count of things in the universe, of real objects in the universe, will be far, far, far less than 2017 to the n. Okay. But yet, you should be able to calculate what the remainder is after you divide it by 51. Part C, another one of these puzzle type questions. Actually, everybody will get the same answer to B. Why is that? You won't all get the same answer to A. Everybody has different ends. You'll get different answers to A, but everybody, when they answer part B, should get the same answer. Even though you've all got different ends right at the top of this tower of powers, but there's something about it that makes sure that everybody gets the same answer. So I want you to explain to me why that is. A little guidance here, your solutions should show how concepts and results in the unit about congruences. So this is all about congruences. Allow you to find these remainders whilst avoiding, as far as possible, explicitly evaluating large integers. I mean, it's not too hard to exactly evaluate this integer. It's within the bounds of something you can do on a computer. You won't be able to explicitly evaluate that integer. You could argue philosophically that this number doesn't even exist, really. Some people would hold that. But anyway. Okay, so question 3 and 4. Question 3 is again about the greatest common divisor. And it also is going to allow you to give an alternative proof that there are an infinite number of prime numbers. Okay, so we did Euclid's classic proof that there's an infinite number of prime numbers. Question 3 will guide you to a different proof of it. I want you to examine this sequence of positive integers, an. An is 10 to the power of 2 to the power of n plus 1. And I want you to prove that all of those numbers are pairwise co-prime. So a set of numbers is pairwise co-prime if whenever you select a pair of different numbers, they are co-prime to one another. Okay? So any selection of two elements from this sequence, as long as they're different elements, they'll be co-prime to each other. I want you to prove that. There's a hint given down here to get you started. The hint is to prove this intermediate result, that an divides 2 less than an plus 1. And then try to extend this intermediate result in a useful way. And then part B is show, having proved part A, then prove that there's an infinite number of prime numbers by making use of the fundamental theorem of arithmetic. When you look at the way we proved the fundamental theorem of arithmetic, we didn't assume there was an infinite number of prime numbers. It was kind of agnostic on that fact. Fundamental theorem of arithmetic says every integer factors uniquely into a product of primes. So using that and this result, that this is an infinite sequence of pairwise co-prime numbers, will allow you to argue a few steps that there is therefore an infinite number of prime numbers. And question 4, again, looking at sequences, this is an arithmetic sequence, xj. So this formula here defines integers x1, x2, x3, x4, etc. xj is defined as this fixed value y plus n times the index j. And I want you to prove that if p is a prime number that does not divide n, then somewhere in this sequence you will find elements that are divisible by p. And to prove this, you're going to need to think creatively about the freedom you have in j. See, j is the index of the sequence. So j can take on any value whatsoever. So that gives you a lot of freedom. You're free to construct a positive integer j in any useful way that you can. So search for a useful way to construct j that will force the element xj to be divisible by p. And the extra bit of information you know is that p, the prime number p, does not divide n. And I want you to demonstrate your argument. See, your argument that there is an element that is divisible by p, it's going to be constructive, meaning that it gives you a method to find the position j where the element is divisible by p. I want you to demonstrate that for, in the special case where p is this prime number, 1.5 by 10 to the 8 plus 1. I give it to you in that form so that you don't make a mistake in counting the number of zeros there, which is difficult to do. Your eye counting a lot of things in a row. So it's 1.5 by 10 to the 8 plus 1. So that's the prime number you're going to use. N is, again, your ID number integer. And Y is the current year, 2017. Okay. Any questions at this moment in time? So it's a mixture of things. Some things are straightforward. We've done examples like them in class. Other things you need to think about. And the one key advice I'd give to you is get stuck into the questions or engage with the questions straight away. Because some of these are things that, you will find useful to think about, in spare moments that you have. And they're the kind of problems that you have to live with a bit. Why is it that everybody will get the same answer to this part C? You've no way of going out and collecting everybody's individual ID number and demonstrating that you all get the same number. There's something about the structure of the ID numbers and the nature of the problem that means everybody's going to get the same answer. Okay, so obviously you'll have queries in the future, so please do ask me any clarification questions you want. I'll measure my responses as appropriate. So I'll hand you over to John now to talk about his questions.
Okay. Now you'll realise why we gave the survey out before we gave out the coursework. Okay. If we go to Moodle, just to start on with, what you'll see I've uploaded, there are 3 files here and a number of text numbers. Okay. Everyone gets an individualized assignment. So there are 3 things you're going to have to decrypt. One of them is the same for everybody, but the other 2 are going to be slightly different for everybody. Okay, so I'll read through the questions and I'll show you the files. Okay, the first one, there's a file called text numbers. It's just an Excel file, and it's got your name and then a text number next to it. Okay, so this will tell you which text you have to decrypt. Okay, there's a second file called Visionaires 2017, and as you probably gather, this is a piece of text which has been encrypted using a Visionaire cipher, which is specific to your text number. Okay, so everybody, it's the same text, but it's been encrypted using different keys. Okay, I want you to decrypt your particular piece of text. If you look on MATLAB as well, on Moodle as well, to help you, because we've done this before, there's a little chi-squared. This chi-squared function is already written. This will do the chi-squared analysis for you if you want to do it via a chi-squared analysis. With all of these, what I'm looking for, I don't mind if you do it exactly the same method that I've used. What I'm looking for is for you to decrypt this. You'll know you've decrypted it correctly because the answers will make sense. If they come out as rubbish, you've got it wrong. Okay, which allows you to go back and start again. I don't mind if you find another cunning way of doing it. Okay, but what I don't want is people using brute force. I don't want you basically sticking this through some machine which just goes through combinations and eventually comes out with the answer. Because this is possible given the key lengths we've got for all of these. Okay, well, if you've got a very, very powerful computer, so it is possible. But we do have this chi-squared stuff here, okay, which is useful for you. Okay, so that's the first one. I'll just show you what it looks like. It's in the Visionaire one. There's loads of them. You pick your one. Write some code in MATLAB would be my advice. Crack this Visionaire cipher. You can do this online. If you go to decode, this will crack this. I've checked this, okay? But I don't want you just going to decode and saying, well, I use my cryptography skills by going to decode and typing this in. That doesn't count, okay? I'm going to want to see how you've done it. If you write any programs, I want you to include the programs. The chi-squared analysis, if you do it in MATLAB, doesn't produce a great deal of output. If you do it in Excel, you will get 26 pages of absolutely loads of information. I will only want you to include a summary of the stuff that works. Okay, please don't print out 26 pages of garbage. Okay, I just need to know that you know how it works. But there are other methods for cracking the Visionaire cipher. Feel free to Google around, try and find out how other people do it. Okay, I've just shown you one method. Okay, second question. You won't be able to do this at the moment, okay, because we haven't really gone through how to crack a Hill cipher, but we're going to do this Hill ciphers next. There's a second file called hills.2017. Again, look at your particular piece of text. This is what I was talking about, the known plain text attack. You know that the first 9 letters say Boria help. Okay, so this is the text that you've got. So I'll show you the file. Where are we? Come back. Okay, so if we look at this, these are the Hill ciphers, and again, what you'll see is you've all got an individual piece of text. Some are slightly longer than others, but not much longer. Okay, there's no advantage or disadvantage in having a short one or a long one. It might take you more than once you've got to here, it's not going to make a lot of difference. Okay, so pick out your individual piece of text based on who you are, and hopefully you should be able to decrypt that. Again, there are Hill cipher decryptors online. I do not believe that you'll find a 3x3 decryptor. You may do, okay, and you can use this to check your answer. But again, if you do manage to find something that will decrypt a 3x3 Hill cipher, if you can check your answer, but you won't need to check your answer because this will come out in English. You'll know you've got it right anyway. That's the beauty of this stuff. If you got it right, you got it right. The last one, everyone gets the same here. There's a Hill cipher. A stream cipher. So if you look at the stream cipher, this is encrypted with a 4-bit shift register. We've been through examples very much like this in the labs. Okay, it's converted into international telegraph code, and then encrypted with a stream cipher using a 4-bit shift register. Okay, again, I want you to decrypt this, describe the polynomial, draw the shift register. Okay, you'll need to do this in order to decrypt it anyway. Okay, and if I just show you the code for this, you look at our stream cipher. We're reading down. So this is the first 5. That's the next 5. I've done it in this format so as it should hopefully make it easier for you to manipulate it if you're going to write some code in MATLAB. But you can do this by hand if you want. I don't mind. Okay, so that's my questions. Hopefully these aren't. We've done these for a few years, stuff like this. This should be a bit of fun for people who like doing this sort of thing as a puzzle. But then again, I'm going to say this: if you're a mathematical bent, doing the number theory things like Killian should be quite a bit of fun as well. So I was his idea about taking your time over these. I always used to think of these when I was an undergrad as bus problems. They were things I thought about on the bus while I was sitting here, and you just not even. No pen, no paper. Just let it run away in the back of your mind. And what you'll see is over the space of a few days, your brain will formulate a strategy. And that strategy will be the key to cracking them. That's my belief. Has anyone got any questions on my one? Anyone any questions? No? Okay.
I'm so happy because
Okay, if you need to speak to us individually, feel free.
Unlike